In mathematics, the Lebesgue covering dimension or topological dimension of a topological space is one of several different ways of defining the dimension of the space in a topologically invariant way. The first formal definition of covering dimension was given by Edward Scheck, based on an earlier result of Henry Lebesgue. A modern definition is as follows. An open cover of a topological space X is a family of open sets whose union includes X. The pi or order of a cover is the smallest number n, if it exists, such that each point of the space belongs to, at most, n sets in the cover. A refinement of a cover C is another cover, each of whose sets is a subset of a set in C. The covering dimension of a topological space X is defined to be the minimum value of n, such that every open cover C of X, regardless of pi, has an open refinement with pi n plus 1 or below. If no such minimal n exists, the space is said to be of infinite covering dimension. As a special case, a topological space is zero-dimensional with respect to the covering dimension if every open cover of the space has a refinement consisting of disjoint open sets so that any point in the space is contained in exactly one open set of this refinement. Any given open cover of the unit circle will have a refinement consisting of a collection of open arcs. The circle has dimension 1, by this definition, because any such cover can be further refined to the stage where a given point X of the circle is contained in at most two open arcs. That is, whatever collection of arcs we begin with, some can be discarded or shrunk, such that the remainder still covers the circle but with simple overlaps. Similarly, any open cover of the unit disk in the two-dimensional plane can be refined so that any point of the disk is contained in no more than three open sets, while two are in general not sufficient. The covering dimension of the disk is thus 2. More generally, the n-dimensional Euclidean space E n \displaystyle\math b caret n has covering dimension n. A non-technical illustration of these examples is given below. Homeomorphic spaces have the same covering dimension. That is, the covering dimension is a topological invariant. The Lebesgue covering dimension coincides with the affine dimension of a finite simplicial complex. This is the Lebesgue covering theorem. The covering dimension of a normal space is less than or equal to the large inductive dimension. The covering dimension of a normal space X is less than or equal to n \displaystyle n. If and only if for any closed subset A of X, if f k s n \displaystyle f a right arrow s caret n is continuous, then there is an extension of f \displaystyle f to g x s n \displaystyle gx right arrow s caret n. Here, s n \displaystyle s caret n is the n-dimensional sphere. Ostrin's theorem on colored dimension. A normal space X \displaystyle X satisfies the inequality 0 less than or equal to dim X less than or equal to n \displaystyle 0 like dim X like n. If and only if for every locally finite open cover U equals U alpha set membership symbol K \displaystyle \mathcalu equals \u underscore \alpha underscore alpha and \mathcal of a space X \displaystyle X. There exists an open cover V \displaystyle \mathcal V of a space X \displaystyle X that can be represented as the union of n plus 1 \displaystyle n plus 1 families V 1 V 2 V n plus 1 \displaystyle mathcal v underscore 1 comma mathcal v underscore 2 comma dots mathcal v underscore n plus 1, where v I equals v I alpha set membership symbol Okay. Backslash display style backslash math cal v underscore I equals backslash v underscore I backslash alpha backslash underscore backslash alpha backslash and backslash math cal a. Such that each v I backslash display style backslash math cal v underscore I contains disjoint sets and v I alpha subset symbol u alpha backslash display style v underscore I backslash alpha backslash subset u underscore backslash alpha for each I backslash display style I and alpha backslash display style backslash alpha. The covering dimension of a paracompact Hausdorff space x backslash display style x is greater or equal to its cohomological dimension in the sense of sheaves, that is, one has h I x k equals 0 backslash display style h caret I x a equals 0 for every sheaf k backslash display style a of abelian groups on x backslash display style x and every I backslash display style I larger than the covering dimension of x backslash display style x. Carl Menger, General Spaces and Cartesian Spaces, 1926, Communications to the Amsterdam Academy of Sciences. English translation reprinted in Classics on Fractals, Gerald A. Edgar, editor, Addison Wesley, 1993, ISBN 0-201-58701-7. Carl Menger, Dimensions Theory, 1928, B. G. Teubner Publishers, Leipzig. A.R. Pears, Dimension Theory of General Spaces, 1975, Cambridge University Press. ISBN 0-521-20515-8. V. V. Federchuk, The Fundamentals of Dimension Theory, appearing in Encyclopedia of Mathematical Sciences, Volume 17, General Topology I, 1993, A. V. Archangelski and L. S. Bontrayagen, eds, Springer Verlag, Berlin ISBN 3-540-18178-4.